Building a modern web application is an exercise in strict isolation. You're managing state, memory, and trust across environments that are entirely disconnected. You have a browser client running on a user's machine, a .NET API server, a relational SQL database, and cloud infrastructure like Azure Key Vault. These disparate systems don't share memory, yet they have to coordinate permissions and pass state back and forth securely in a matter of milliseconds. To understand how this actually works in practice, we are going to trace the lifecycle of a single authenticated HTTP request. Following this packet from client initialization to database read and back exposes the exact execution order and dependency rules required to keep an enterprise architecture from collapsing. It starts at the client edge. When a user navigates to a protected page, the React component mounts and triggers an initial data fetch. To ensure this fetch only happens once, we use a useEffect hook with an empty dependency array. Without that empty array, React would run the fetch on every render, creating an infinite loop of network requests. Before sending the request, the client retrieves a JSON Web Token, or JWT, stored in the browser's local storage, and attaches it as a bearer header. A JWT consists of three parts separated by periods: a header, a payload containing user claims, and a signature. Notice the payload is only base64 URL encoded. It is not encrypted. Anyone intercepting this token can decode and read the contents. Because of this open readability, you can never store sensitive data like plain text passwords inside a JWT payload. Instead, the backend handles the actual password verification during the initial login step, comparing the user's input against a stored hash using bcrypt. Bcrypt is deliberately slow and includes built-in salting. Even simple hashing algorithms like SA256 are too fast, making them vulnerable to brute force and rainbow table attacks. Bcrypt's computational cost neutralizes that threat. Once logged in, the client edge relies entirely on these verifiable, stateless tokens. It can prove the user's identity to the server without ever holding the actual credentials. The request packet leaves the client and hits the API's network perimeter, where it immediately encounters CORS. CORS, or Cross-Origin Resource Sharing, is a security mechanism enforced by the browser. It prevents a malicious website from silently making API calls on behalf of a logged-in user to steal their data. Developers often configure CORS with Allow Any Origin to bypass local errors. Once you introduce authentication cookies or tokens, this becomes a severe vulnerability, allowing any site to piggyback on the user's active session. The production standard is strict whitelisting. Using with origins, the API explicitly permits requests only from the specific URL of the React application, blocking all others. Once cleared by CORS, the request enters the .NET API. ASP.NET Core processes requests using a strict middleware pipeline model. This pipeline is a sequential in-and-out tube. Every operation must execute in an exact, non-negotiable order. A critical rule is use CORS must precede use authorization. If authorization runs first, a request lacking valid credentials gets rejected before CORS headers are ever added to the response. When that happens, the browser sees the missing headers and throws a CORS error. The developer wastes hours debugging network origins, when the actual problem was simply the middleware order. Assuming the order is correct, the request reaches the auth gates. First, authentication validates the JWT signature to establish who you are. Then, authorization checks that identity against specific rules to determine what you are allowed to do. At the network perimeter, security requires writing the right code, but it equally requires executing that code in the precise chronological order. With identity confirmed, the authorized request moves past routing and enters the API's dependency injection, or DI, container. Here, the architecture separates its concerns. Controllers are kept thin, handling only HTTP status codes and routing. The actual business logic lives in dedicated services, so it can be tested in isolation. To manage memory, the DI container assigns these services one of three lifetimes. Transient creates a new instance every time. Scoped creates one instance per HTTP request, and Singleton keeps one instance alive for the entire life of the application. Any service that interacts with the database must be strictly registered with the scoped lifetime. This requirement exists because DB context is not thread safe. It tracks entities for a single operation. If mistakenly registered as a singleton, concurrent HTTP requests hit the exact same memory instance simultaneously, causing overlapping queries and fatal database corruption. By using a scoped lifetime, ASP.NET Core guarantees that every incoming request gets its own fresh, isolated instance of DB context, which is safely disposed of the moment the HTTP call ends. Dependency injection serves as a necessary memory isolation mechanism, ensuring stateless web servers remain stable even under high concurrent load. Inside that isolated memory scope, the service reaches the data layer. The D context manages the connection and tracks entity states until save changes is called. When looking up a single record, the method you choose matters. Find checks the in-memory cache first for maximum speed. Single or default skips the cache and queries the database, throwing an exception if duplicates are found to enforce strict business rules. But when retrieving lists of data, developers often encounter the N+1 query problem, a silent performance killer. This happens when fetching a list of entities, then looping through them. Lazy loading triggers one initial query plus n separate sequential database hits. The solution is eager loading. Appending the include method performs a single unified join operation, retrieving all related data up front. The database executes the query and returns the raw, tracked entity framework model back to the API service. Before sending this data to the client, the service must reshape this raw entity into a data transfer object, or DTO. DTOs shape exactly what the API sends or receives, hiding internal fields. Crucially, they prevent over-posting attacks, where a malicious client injects extra JSON fields in an attempt to modify database columns they shouldn't have access to. The DTO acts as a final structural firewall. It ensures the public API contract remains strictly decoupled from the literal database schema. Before the DTO can be returned, we have to address a hidden prerequisite in the infrastructure. How did the APIs securely obtain the database connection string in the first place? In our cloud setup, Azure Static Web Apps serves the compiled React frontend via a global CDN, while Azure App Service hosts the .NET API backend. If you commit a hard-coded production connection string to your source control inside appsettings.json, anyone with repository access can read your database credentials. The Zero Trust solution is Azure Managed Identity, which eliminates the need to handle passwords or static keys entirely. Using default Azure credential, the app service authenticates to Azure resources as itself. The code automatically detects the environment, seamlessly using local credentials during development and the managed identity in the cloud. When the API boots up, it reaches into Azure Key Vault to pull its configuration. Following the principle of least privilege, the application is explicitly granted only get and list permissions. It can read the secrets it needs, but it cannot alter or delete them. Modern infrastructure security relies on applications securely proving their own identity to the cloud, rotating away from static keys that can be leaked or stolen. Having safely queried the database, the fully shaped DTO payload leaves the API, traverses back across the network, and lands safely in the React UI state. Throughout this milliseconds-long journey, strict boundaries protected every layer. At the edge, the browser enforced CORS, while the client verified identity using a stateless JWT. In the backend, the strict sequence of the middleware pipeline blocked unauthorized access, and the scoped DI container isolated memory to prevent database corruption. And beneath it all, Azure Key Vault enforced zero trust authentication, ensuring the infrastructure itself remained secure. Full-stack engineering requires mastering the exact boundaries, life cycles, and execution orders where these disparate frameworks intersect.